So I'm Zdenek from. You asked me. Yeah, from Max for Detectors and Scientific Software. I am working on, besides working on other things, we have a project about FPGAs and like data reduction using FPGAs on with high-level languages. And I have for the first time a no-bugs conference, and I was thinking what I should put there. And actually this year we were facing with going on DevCloud out or on the cloud. So I thank for this contribution. Thanks for giving me the opportunity to say something about it. Oh, which one? Can move things. Not move. Okay. Good. So it should not be a talk for electronics engineers, not also cloud engineers. It is also not containing like details of our async bin count project for the data reduction, and it's not an advertisement or machine telecommunication. Until now, I have never met Intel salesperson. Yeah, so that's on the other side. Like I am like more like a data scientist. Is using high level so I'm looking on high level tools for data analytics with FPGAs for X-ray data. This will contain a quick overview of available cloud services of FPGAs. It is a view of a software developer on usage of a particular cloud out and report on benefits that this can bring. I'm always also saying something about how FPGA data analysis has appeared at Max 4. It started many years ago when I met Arthur by a coffee machine and he was like a physicist from CERN. And at that time, IT team leader at Max 4, and we were discussing that we would like to write a project with scientists about reduction of data in real time on GPUs, and he was asking why we are not using FPGAs, and I am sure that I found at least 10 reasons why we are not using them. But this didn't stop us to continue. We met smart people from the other side of the bridge, at Copenhagen University, who are really FPGA experts. It's now there is Andriy Salnikov also helping me with many projects related to FPGAs, including the faithful collaboration with Filip Leonarski here from PSI, who is developing a Jungfrau project for data acquisition and data processing for MX data, mathematical crystallography data. As I was saying, we are doing high level. I am using high level languages. I am not an electronic engineer, so I'm, for example, for programming FPGAs using OpenCL. There are other approaches like high level synthesis or Kenneth. Is an author of an approach called synchronous message exchange. So this is all almost like C type languages. So CME you can write in C#, yeah, but the type of programming is different. Otherwise, it looks like C. And then we are orchestrating everything from C++ and Conda, and the whole thing is based on that you write code in this high-level language, which is then transcompiled to some hardware description language, and that is then synthesized to bitstream. This is a very complicated process, but I even do not know details, but it's not important here. What is there any software for FPGAs for data reduction and analysis, like for photon and neutron science? Surprisingly, yes. Philip is developing here at PSI the data acquisition and data processing software for mathematical crystallography, which contain also spot finding on FPGA. Maybe not now. Maxime Martelli already several years ago implemented a tomography reconstruction on OpenGL on FPGAs. Using OpenCL, and now we at Max 4 have a project about creating this nice powder diffraction patterns by integrating 2D detector area data by azimuthal integration. Yeah, that also works on FPGAs. So, now I skipped too much. So what does matter? Yeah, no, not. So the thing is that now I was thinking like clouds, yeah, or how clouds are helping user group better software, and it is I think that they are supporting a lot collaboration and teamwork, issue tracking and version control. We are all working on Gits and various instances that are all in clouds. Yeah, we are implementing a lot of our continuous integration in clouds. We are using testing and sandboxing for clouds. Yeah, and so this is how they influence the quality of the software. And I did also science practice. This is where I put up one point, and it's reproducibility, that we are working on clouds to improve reproducibility. For me, like just implementing continuous integration in our project, that brought us the advantage that we have multiple configurations for different hardware and different software framework versions. We also have artifacts, logs, bit streams, yeah, notebooks. Yes, so that's a big profit. On the other side, with this piece of continuous integration, is, by the way, a lot again inspired by a project of Philip. When I saw how nicely it was here at PSI, I had to do it also at Max 4. And but typically we implement this continuous integration on our private edge clouds in the facilities. Yeah, so I was also looking what are the requirements when you are developing FPGA software. Yeah, you need some general software for like orchestration of everything, like running the software program. Yeah, then you need a development kit. Yeah. In my case, it's Vartus, who's for this you need where you are doing like when you are compiling for emulation or for hardware. Yeah, then you need some board support package, any for emulation to create just simulation on the CPU, and then you need a specific board support package for the hardware if you want to make hardware. Yeah, like over the big stream, and actually you need the hardware, like the board for testing when you are testing on hardware. That's to my opinion, the table. There are two interesting things. Hardware you need only when you test on hardware, and it is a 3-minute task. So you need the hardware only for a very short moment. Yeah, and next, of course, the largest step is compilation of the workflow for hardware, which can take from 3 to 12 hours, and they require often tens of gigabytes of RAM and multiple cores, not usually more than 8. And but it is good to run. You can run several hardware synthesis in parallel. Yeah? So when I'm looking on this table, I cannot. This is an excellent thing to run in the cloud. Yeah, because you have an extremely expensive resource, and you need it only for a short moment. Yeah. So another reason why maybe to go to cloud is that there is a very long. There can be a very long delay between you decide that you go for an FPGA-based project and you can have a working installation at your facility. Like very many steps that are on the way, including ordering, lead times. Then also setting server, finding licenses, installing the whole ecosystem, yeah, can be very long. And this is why it is good to go for cloud. So I have very many reasons to do continuous integration. I wanted to also find some other hardware, some people are saying that using cloud can be even more cheaper than, of course, buying expensive hardware. That then there is a risk that something will break. Actually, one of the reasons was that one of my developer cards has got broken, and I was looking for how to replace it quickly because it was like a long-term issue. Oh, of course, cloud can help you to skip some barriers. And I was also curious because we are within Expanse project developing cloud for photon science users. And I was curious how can look at cloud for me, like for a software developer. Yeah. So are there any clouds for FPGAs? You can, of course, search, and you will find that there are papers about clouds on FPGAs. There are also review papers about them. There are FPGAs in the Amazon cloud, in Microsoft cloud. Yeah, and there are clouds for LabVIEW users. Yeah, I was also lucky and found an excellent source, like Professor Jakub Schäfer at YAL. He's clearly running a course directly on cloud FPGAs. And there is a lot of materials available in his course. the course is just running. So but the problem is that if you Google this and to find that his course, the PDF material will be appearing how the course is like proceeding. But you can go to the older course, for example, from 2019, and you will see the all material immediately. There's a lot of information, more than I can squeeze in this very short presentation. This is an overview of clouds that are supporting FPGAs. Like if you are not familiar with FPGAs, then there are two companies who are like ruling the market. The first of them, the strongest one is Xilinx, which is now AMD, yeah, and then this was Altera, which is but that Altera was taken many years ago by Intel. So this is why I distinguish two types of FPGAs, Xilinx and Intel, and I'm looking on the clouds containing them, because the cloud must also fit approximately our needs, and we are using OpenCL. Our thing is optimized, like from the beginning it was designed for ARIA 10, but we would like a little bit more FPGAs of a newer generation, for example, Stratus. So yeah, look, there are clouds having Xilinx card, there are Amazon, yeah, there are clouds having both of them, there are Shadow, and there are clouds that are having only Intel, they are green. Alibaba has what I need, but it's that would be interesting. Then there is other clouds. I choose the Intel DevCloud. Yeah, so let's go to Intel DevCloud. And when I land to the Intel DevCloud out page, like the one from Intel, I'm always unhappy because I feel bad that I cannot find what I now. But the best way how to go there is over simply GitHub. Go on GitHub on Intel FPGA DevCloud. They have external documentation there, plus things how to do it. Yeah, you need to register as a customer. I'm not a big customer of Intel, but that is used to send you instructions via email, and also for single sign-on on the Jupyter Lab. Then you can you receive a key that you install, and you are ready to go to SSH Jupyter DevCloud, or you use the Jupyter Hub. If you go over there, Jupyter Hub, then you see that they have the same type of things how you can access the system. They don't have a remote desktop as we often have. So they have SSH login nodes where you can start job, and they have like Jupyter Labs on Jupyter Hub on shared notebooks. OpenCL Intel instances are not included in the in the Jupyter Lab instance, so I prefer to use SSH. So I actually SSH to the DevCloud. This video should take 2 minutes, and it's one of the last slides. Yeah. So then you have to source. It's a very well described. Then you do this will load some support script, and you have this instances that you can choose. I choose the instance number 1. It submitted a job. Yeah, so it's a little bit helping me that I do not know how to know a lot of these parameters. I'm on a node. Yeah, I have to source again the software. We at Maxwell do it. For example, is modular load. Yeah, they use source. There is an accelerator on that group on that node. I have still to load some software environment, and now I'm ready actually to compile for emulation, which I will do. No, I will first go to my project, and I will compile for emulation. Yeah. Then in the next step, I will likely as a support software I'm using Conda. Yeah. So I will load a Conda environment which is pre-installed. Then I will I will activate a proper environment that you can find on the web of the project, and I will run emulation. After running emulation, this thing will reprogram the FPGA, which will take few seconds. Yeah, and run a Jupyter notebook, it will take 3 minutes. Maybe I will stop that. Yeah. So now it is using Conda to activate Conda environment, and we will then start emulation in the Conda environment. And I will quit it after emulation. Yeah, so it's running emulation. And then running the notebook would take 3 minutes. So that's no, but it's cutting the video. So the emulation has happened. Yeah, I know, we can leave it. I will go to the next slide if I can. Yeah, so, and the result, what was like outcomes of going to cloud was that I consider Intel DevCloud as a very exciting place. Yeah, I cannot compare with anything else. Like as I mentioned, we in Expanse have a similar activity of building cloud for photon science users, and I'm surprised that Intel Cloud is actually using this DevCloud is using exactly very similar tools. So which is saying to me that we are on the right way. Like a negative or neutral outcome is that I didn't find a way where to run a CI for my mainstream repo that is public. So this I would really need to go for another cloud because I think this one is not it's not intended for this purpose. I got access to a hardware that I do not have, which is extending our project. Then I have been forced to better organize my project. I increased the flexibility that I have because when something on the facility is broken, we can continue developing here. Yeah, and there is a good reference implementation, for example, suitable for benchmarking. In future, there is possibility to go for one API if one wants. And what is the most important outcome is that now the project is much more accessible to the broad community. People can simply try it without buying an expensive hardware. That's all. Thank you for your attention.
Okay, so are there questions? Yeah.
You gave an example of learning 3D reconstruction with FPGA. Do you know how long that was taking and how many frames?
Example of 3D reconstruction at the beginning. Yeah, that was paper written several years ago with the guy, I forgot the name, from CNRS. I think I can give you a link to that paper. It's already older paper. He was using the same card. And I would say that at that time, he found a conclusion that FPGA for the tomographic reconstruction is not faster than at that time existing GPUs. Yeah, now we have much better GPUs. We have also better FPGAs. But on the other side, I am also saying, and this is why I started with the project, is that we should look for another ways how to do things. Yeah, if you implement back projection, which is heavily matrix multiplication, yeah, you on a hardware like FPGA, then you will be competing with GPUs that can do this also very well. Even GPUs are not intended for matrix multiplication actually, but on the other side today there can be again a changer because like these FPGAs that I was showing mainly in Microsoft Cloud, they have already special units that can do submatrix multiplications. Yeah, with floating point like arithmetics. They have like 18 times multiplier, like DSPs inside. Simply the electronics that is doing just that, so it does not need to be implemented in FPGA. So it's very that paper is already quite old. Yeah.
I am sure you're not the only person in the room who's tried to do the FPGA program and found the documentation impenetrable and so forth. I wonder if it would be good if there was a way we could share notes on this kind of stuff so that people have a head start, not just on the code and the projects, but even the basics of how you work your way through the Intel DevCloud.
Yes, I think that documentation is excellent. My plan would be if somebody would like to contribute, the project is public, open under open license. You can, like it would be nice to write it like a notebook, the whole workflow. Yeah, I would be very, it would be very grateful. Yeah.
Okay, thank you.